communication theory. Once I can get this thing to work.
Should we sit facing this light?
Yeah, I'll make it work somehow.
And then in case we want to use the whiteboard, get this kind of
Yeah. Well, welcome.
report.
Yes, hope everyone's assignment 4 is in by now, because it should be, because we are on a tight schedule. If it's not in yet, we have some news for you. Next slide real quick.
Okay, so far, out of 22 members, only 9 of them have submitted their assignments, and they've been consistent with the deadlines. So I don't know what the other 13 people are doing, but this is definitely not a good stats, especially given that you had 1.5 months to complete these. And we told you to set up meetings with us over the break. We had work sessions, we had lab hours, and yet some people didn't even get started on assignment 4. Let's see. So I'm gonna name some people. No, don't worry. Let's see. Courtney, Jason, Thomas, Caden, Ethan, Nabil, Zaire, Grace, and Saad. I'm satisfied with your work on hardware. So you guys are welcome to join the hardware team. Now I know that Jason and Caden already told me that they want to do DSP, so you guys have the choice. If you want to switch to hardware, the deadline for that is this Wednesday, so let me know. The rest of the people who I didn't name, that means you didn't complete any of the hardware assignments. So I'm not going to let you into hardware, unfortunately, because like I mentioned at the beginning of fall, at the end of fall, deadlines matter, especially in winter, and if you haven't been consistent, it's not going to work out. Let's see, next. So what's going to happen is that you will be placed in the DSP team for now, and then we are going to do the same evaluation at the beginning of spring quarter, this time for your DSP assignments. And if Nathan is not satisfied with your DSP work either, you will be dropped from the project. The people who I named who are also willing to participate in the hardware, you guys don't have to do the DSP assignments. I don't expect you to do those. However, I will assign you some new hardware research tasks. You are more than welcome to do the assignments as well, the DSP assignments. We will definitely help you with those, but we won't hold you accountable for those. In terms of the timeline, we are going to do some R&D, which is going to last until the end of week 4, and then I'm going to set up some weekly meetings to touch base with the hardware team. Given that we don't have that many of you here right now, that we'll probably talk about it some other time. So yeah, that's it for the hardware.
I think one more thing to add for the hardware is we have also a parts order due around week 6. So right after you finish your R&D, you guys will go into PCB design, and that will need to be probably done by week 6. This is to give you perspective of where you're going with it. And from there, we order and build. And so best of luck to all you hardware folks. And the rest of y'all are with me. So we'll be having some fun, like we'll see today. So today we're gonna talk about communication theory, and what we're gonna talk about is just how we encode signals and different ways to do it, and how we can send our signals from one end to the other, the transmitter to the receiver end, while minimizing our signal to noise ratio, which is how strong our signal is compared to the noise, along with other techniques to make sure our signal is properly transmitted. To give a brief overview of what the system is like, we have some bit signal that we're gonna send, and it goes into, we're gonna map it to a bunch of symbols. Symbols we'll talk about in a second. Goes through a filter, and then we modulate it. So say our bits and symbols vary at, say, 20 megahertz or 20 kilohertz. We modulate it up to 1 megahertz, which is what we're actually transmitting at, or the microcontroller is going to be sending at. And you get noise in your system, demodulate, have another filter, and put it back into bits. And hopefully at the other end, we get the same signal we have here, even with all the noise in between. So to start off with, we're going to talk about modulation. So there are 3 main ways you can encode information in a signal. One is its amplitude or frequency, so we'll start with that, which is, say you have your signal is A cos of omega t plus phi. Frequency would be to change that parameter. That's typically done through hardware. For example, if you were to make a diode and reverse bias it, you can change the capacitance of the diode, and therefore you have a voltage controlled way to change the frequency at which you send a signal. Another way is amplitude. You guys kind of already do that in your amplifiers and mixers and things like that. So, and then you have phase, which is you modify the phase component, so it can be at 0 degrees or 180 degrees. And the way you map these changes to bits is arbitrary. And you can actually generalize this quite a bit. So one thing that we're interested in is how can we take these forms of modulation and maybe perhaps transmit more information, generalize this a little bit. So first thing we're going to talk about is we're put it in the frame of complex analysis and look at it in what's called a constellation diagram. For our analysis, we're not going to be doing any frequency modulation. So we're just going to be doing phase and amplitude modulation. And doing phase and amplitude modulation, you can take your signal and put it in a phasor-like notation. So if you look at our math over here, we say x of t equals the real part of our amplitude, which can vary, times the complex exponential of some frequency plus our phase, which can vary. You guys may already be familiar with this in EE10 or 101A, but just to reiterate it, we take this signal and we take out the frequency component. So you separate the complex exponential into 2 little exponentials, and we're going to treat the non-frequency part, meaning the amplitude times the phase, as one component. And since our whole system is linear, we can do all our math with this one complex number, and it's going to work out the same, and we can modulate it back. Okay. So this complex number is called the baseband signal. Why? Because it's low frequency, and that's just mostly it. It's low frequency, it's where all our information is stored. And our baseband signal is going to have 2 components, an in phase and a quadrature component, an I and Q component. And we can see what that kind of looks like over here, right? So in a normal amplitude modulation, you can have 0 be some voltage, 1 be some voltage, right? So on this complex plane, we have no Q component, no imaginary component, because we're only modulating the amplitude. So it's only these 2 points. And these 2 points are called our symbols, by the way. Symbols, which is basically means representations of our signal that represent some packet of bits. So in this case, it's one symbol represents 0, another one represents 1. In the case of BPSK, which stands for binary phase shift keying or something like that, we have 2 points over here. And what BPSK does is you take your signal and you have actually a constant amplitude, but your phase varies by 0 and 180 degrees. So this kind of makes sense because if you have cos of omega t plus phi, and phi is 0, then you have cos of omega t. And if phi is 180, you have negative cos of omega t.
We have this is the representation.
Yeah. So if you're do this with like a square wave, yeah. Right?
Yeah, so you can see like the phase of the signal changes. Like here, this could be 1, and then you can switch to 0. So now you're 0. This is double the length of the first symbol. So this looks like 1, 0, 0, and then again switch to 1, and then again switch to 0. So you see the phase encodes the information.
Mm-hmm. Yeah. Thank you for going back to that. Another way we could do this is also, we could have a phase of 90 and 270. And then on our constellation diagram, we have our symbols here and here. Symbols or bits there and there. So as you can see, we can very well represent how we modulate our phase and our amplitude on a constellation diagram. Yeah, I think that's all to say. Okay, so we can take varying our amplitude and our phase, and we can generalize this a little bit more. So of course we have our very basic BPSK, but we can take that and we can now, we can have we can represent 4 symbols now by taking, by mixing how we modulate our amplitude and our phase, okay? And we'll talk about a little bit more how we can do that specifically, but for now, high level, you can have some magnitude in your I component and some magnitude in your Q component. And by basically modulating some amplitude in each direction, you can express phase and amplitude. And we'll get a little bit more into that. This is an even scarier way. We won't be doing that, or this. We'll be doing this in our actual project. But I think it's good to have a more general understanding. To create these mappings though, this is what you call quadrature amplitude modulation. And that's how, and actually let's dig a little bit more into that. Next slide. And so mathematically we can express this as follows. We have our base signal, x of t equals a of t cos of omega t plus phi of t. And we can use trigonometric identities to break it up as follows. And so what we say actually in the end is this part. We say I of t is going to be this component and q of t is going to be this component. Okay. And so if we were to take these signals, if you go back a slide, what that would look like is you can have your I of t change from 1 to -1, and your q of t change from still 1 to -1, or j to -j in this case, because that's the complex look at it, and create this kind of mapping. And that happens by taking your I of t, multiplying it by a cosine, then adding it with your q of t times a sine. That's how you can physically realize that. So go back to the other slide. And just to give you a little bit more sense, this actually matches our phasor notation of the complex baseband, I of t plus jq of t. If you actually look at this and try and work it out yourselves. Actually, let's take a moment and on the whiteboard. This should pan out, because if it doesn't, then we have bigger problems in the foundations of math. But through trigonometric identities, we saw that x of t equals I of t, cos of omega naught t, minus q of t, sine of omega naught t. Where I of t equals A of t cos of your phase and Q of t equals A of t sine of your phase. Alright. So going back to the first thing we brought up, where x of t equals the real part of A of t e to the j omega naught t plus theta of t. Expand this to the real part of A of t cos of omega naught. Let's look this. E to the theta.
Yeah,
What's up?
J.
Theta, yeah. Of t. Times e to the j omega naught t. Can you guys kind of see how these two forms of analysis are equivalent?
So basically, to give a summary of what just happened, we know that x of t, which is our wave, is, as Nathan mentioned, it's a, which can vary with time, and then cosine of omega naught t plus some phase. This can also vary with time. You have control over this part and this part. This omega naught is that carrier frequency, that's your 27 megahertz times 2 times pi. So you cannot change this. Hardware designs this, and we have the control over it. Now, the two parameters that you can change is A of t and theta of t. Now, what we have here is we are saying, okay, I can represent any wave, which is x of t, in this way, just using trig identities. And when I represent it in this way, I already know what my carrier frequency is. So the carrier frequency given, all I have to do is to give you I and Q, which is these two. Yeah. Now, the beauty of this is that this no longer has a high frequency. So theta of t can be a small angle. A of t can also change slowly. So that's why we call this baseband. And here you can encode this AT and theta t information into this complex form, which takes place on your complex plane. And then you say, okay, these are my symbols, for example.
Yeah. Another beauty of this is you think, can you actually go back to the previous slide, or next slide of me? You would think that if you, or previous, sorry. You would think that if you wanted to, that works, yeah. If you wanted to achieve different points here all around, you'd need to have some kind of complicated way to change your phase and your amplitude, right? What's the phase over here, right? Then you change the phase here, change the phase here. We don't necessarily have to do that, because as we saw over here, another, actually never mind, I take that back.
No, I think
Well-
that's fair. Yeah. So basically, the distance from the origin. I'm doing some Stanley Kubrick stuff. So the distance from the origin on any of those represents this amplitude, and then you also have that theta, which is, so if we look at this here, these 2 points, for example, what is common between these 2 symbols, theta or the amplitude? Theta is the common, because if you draw the line from the origin to the symbol, this theta and this theta is the same, and then the amplitude is different. Whereas between 0, 0, 0 and 1, 0, 0, 0, same distance from the origin, so A is the same, whereas theta is now different. Now, what are we doing for VPSK, which is what the project is going to be? So what do you think we are changing? We're changing the phase, because the amplitude, the distance from the origin to each one of these symbols is the same.
Yeah, I mean, you could also very well change the amplitude to between
Yeah.
1 and -1, because it's still equivalent, but yeah, there's just 2 ways to go about this, I guess.
All right.
One more thing I want to talk about is why these diagrams are shaped the way they are. So this is, I guess, it's a seemingly complicated way to achieve different bits on your constellation diagram. Let's say I wanted to encode 16 bits, right? Or 16 symbols. If I were to do it only through phase modulation, it would look, man, my space is gonna be bad. Okay, pretend this is 16, okay? I did 16, okay. Pretend that's 16. Maybe it is, maybe it isn't, who cares? Okay? What we care about in the end is the distance between these two. Why? Because noise is going to affect our signal, and it's going to shift these, back and forth, right? And so if you want a certain separation to demand a certain tolerance of noise, for this kind of characteristic, you need it to be much farther apart. Meaning, the distance from here to your symbol, which is the energy required to send your signal, needs to be much larger. Versus over there, on the screen, the 16 PSK, you can have good distance between your bits or symbols while still being able to send it at low energy. So that's another advantage of this more complicated scheme. All right. Okay, so we send a signal like this, and this is going to be our transmitted signal, right? A little bit more complicated than a simple sine or cosine, but this will be our transmitted signal, okay? So the next question is, how do we take this and demodulate it on the receiver end? And it's actually, okay, let's talk about it. So what we do is we can take our signal to get the I component, we can take the signal and modulate it by a cosine at the same frequency as the transmitted signal, okay? And what happens is it gets squared, then you have a cos and a sine on the Q component, and you can take trigonometric identity, the cos squared identity, to break it up into this, 1/2 plus 1/2 cos of 2 omega t. And for the Q component, this is the double angle identity where cos times sine is 1/2 sine of 2 omega t. And we take that and we can low pass filter it to get rid of the high frequency. And what you get is just your I component over 2. Similar thing for your quad, to obtain your quad component, you modulate it by negative sign. Again, cos times sine, which is sine of 2 omega over 2, and sine squared, which is 1/2 minus 1/2 cos of 2 omega. Low pass filter it, the 2 omegas disappear, and you get q over 2. If you really wanted, you could take, actually not if you really want, you actually will do this. You're going to take your, once you know your I and Q components, you can find your amplitude and phase, because you know how that maps to your symbols. I guess you can go either way, so it doesn't matter. But yeah. Yeah. Do I need to take a pause real quick for you guys to go back to side just real quick? Oh wait, any questions so far actually?
We realize this is too much math, so feel free to come to either my lab hours or Nathan's lab hours, and we can just walk you through what the math is.
Yes.
But the main takeaway is that what matters in a signal, which is x of t times cosine of omega naught t, is that you can represent it as an I and a Q component. And then once you receive that signal, you can decompose it into I and Q, and from that you will get the information.
Okay.
Good to go.
Okay, so you might see this here and there if you do work in communications. This is a graph that kind of reflects how much error you get in your signal versus the power you send it at, okay? And so what these different plots are different communication schemes. So for our lowest we have BPSK, for our highest we have 256 QAM, which is, imagine that constellation diagram, you have 256 dots in there, okay? And the main takeaway of this plot is you can have use schemes, communication schemes, that have less symbols, right? Less ways to map bits, okay? And they're gonna have high resilience for a very noisy environment, right? EBNO is your signal power over your noise power. So the higher EBNO is, right, that means a higher signal to noise ratio. So if you want to achieve a certain bit error rate, like for example, you want to achieve a bit error rate of 1 times 10 to the negative 6, for BPSK it's about 10 dB versus 16 PSK is around 21 dB, right? That's almost double the power you need. So there's actually a trade-off between all these constellation diagrams. You can either have high resilience of your signal if you have a noisy environment, or if you don't have a noisy environment, you can have a bunch of symbols. And remember, each symbol represents a number of bits. So for your higher order constellation diagrams, one symbol could represent 4 bits. So that means you'd have higher throughput, higher data rate. So there's a trade-off between this. And this is again visualized through this over here. Like I mentioned on the whiteboard, you have your symbols, and noise has this kind of effect on your symbol. It's going to fuzz it a little bit. And so these graphs are understood by knowing when does noise cause this dot over here to be in this thing. So when is it misinterpreted? Okay, any questions so far? Cool. So we can take bits and we can map them to symbols, as we see in our constellation diagram. And knowing how they map to symbols, we can figure out how we can modulate our amplitude and our phase in our signal, such that we can send that signal over some channel to a receiver end. But what we haven't talked about, one, is how to shape our signal, okay? So far, what you've seen is you shape it through a square wave, but it turns out that's not a great way to do it. And then we're also gonna talk about why we would have a filter on the receiver end, okay? Next. So, start with this, I guess. So we're going to take our baseband signal, our symbols, which we can express as S of t, and we're going to convolve it with some kind of other function, which is going to be our pulse filter. And that's going to affect the way our symbol is shaped. So for example, we could use a square wave, as we did before, and we take that square wave. This is actually convolved. Actually, let's go whiteboard. Let's go whiteboard. We were to snare symbols, DGSK, are like this. Okay. This would be, say, 1, 0, 0, 1. This is what our symbol signal will look like, okay? And then we take this and turn it into a signal, right? So before we modulate this, right, we need to make this a little bit more, before we mix it, it has to be continuous. So as we see on the screen, we're taking a square wave. So once you convolve it with a square wave, it becomes this, or like this. Okay. And this is a straightforward way, or a very intuitive way to make your signal analog before you mix it. But this is problematic because we have band, what's it called? Band limit requirements, right? For us, we need to stay within like about 27 megahertz to 27.1 megahertz. That's a very small range to be in. The Fourier transform of a square wave is infinite, right? It's a sinc function from negative infinity frequency to positive infinity frequency. And so a square wave is actually not a viable filter that we can use. So the next thing that might come to mind is, what if we take our signal and we make the pulse shaping filter a continuous signal, right? It goes from negative infinity to infinity. Because if a signal is short in the time domain, it's going to be long in the frequency domain, and vice versa. So if our signal spans from negative infinity to positive infinity in the time domain, it what do you say? It's going to be short in the frequency domain.
Like a sinc function.
Yeah.
Basically.
So actually, if we make our pulse filter a sinc function, then in the frequency domain, it's going to be a square wave, or whatever you call it. And now we're going to meet our band limit requirements, which is good. you could actually almost call it a day, but we can do a little better. Right. So, okay, one problem with making our symbol continuous in the time domain though, is this thing called intersymbol interference. And as you can imagine, if it's infinite in the time domain, then it's going to, then bits will overlap with each other, right? For example, if your symbols are like this, right? Again, same situation. And our pulse filter has some arbitrary Fourier or time domain representation. Then it becomes clouded, right? All these added together make the representations at each bit very unclear, right? The new representation could be something like this, or right? So then we look at it, what's a 1, what's a 0? It's hard to tell. This is what we call intersymbol interference, right? Each symbol is interfering with each other, and your mapping becomes unclear. Well, then now what do we do, right? Our signal is infinite in the time domain, or pretty long in the time domain, to make it very short in the frequency domain. But we can't have it the other way around because then we don't meet our band limit requirements. One way you can get around this is actually like through a sync function. You could use that. Or you can use other more special functions. So a sync function if you guys recall, sine of, we'll call it pi t over pi t, just to make this easy on me. Okay, so the sync function goes to 0 every t equals 1 plus k, okay, where k is an integer. Okay. So plotting our sync function, it looks something like this. Okay. At 0 at those intervals. So then if we wanted to make sure that we recover our signal correctly, right, without the bits becoming confused, we could send our symbols at every second, right? So going back to this, if we send, I have 1 symbol every second, and once we convolve our symbols with a sync function, then we're going to get the following waveform. Okay, and I'll just draw this out like this. that's quite messy. But I hope you can understand that all we have to do is sample right. Sample at the right time. Because the magnitude of each symbol occurs at when the other symbols are 0, right? The resulting waveform of this would look something like this. Your 1s and your 0s are more or less clear. Doing this technique is also called the Nyquist intersymbol interference criterion. Going to the math, again, this is just like a mathematical way to express it. It's 1 when you want to sample, 0 when you're not sampling. Right? Or on like 1 on when the symbol should occur, 0 when it's not occurring. This is a frequency domain representation, but I don't know how to give you intuition for that. You can just look at it. Okay.
Wouldn't that still have interference from like the next signal after one decided?
Right. Sorry. So what that meant was, okay, it's going to be 1 when the symbol does occur. So a sync function is 1 when it does occur, right? But when the next symbol occurs, right, which will be at 1 second, it's at 0.
But then after that,
0
the next
again.
seconds.
And then 0 again. And it's 0 every 1 second because of the sign of pi t.
Oh, okay.
Okay, yeah, so it'd be like, yeah, every 0. So it's a nice function to have. Yeah. The sync function is actually an okay function. Like it works for what we're trying to do. But people have made more specialized functions to make it even better. So this is called the raised cosine. And what the raised cosine is well, it's defined by its frequency domain representation. So it's basically a generalization of your sync function, right? It's a piecewise, and the main parameter of it is this factor called beta. And beta is called the roll-off. Okay, so it's how quickly it rolls off. 0 meaning it rolls off very quick. 1 means it rolls off slowly. Okay. So at beta equals 0, you just have a normal square wave, and then the more we increase beta, it's going to become more smooth. Okay, or yeah, smooth is an okay word. And beta is a parameter that varies between 0 and 1. Okay. So why is this kind of useful? Now we have a way to tune not just how fast this rolls off, but also how fast it rolls off in the time domain. At beta equals 0, you have a normal square wave, a normal sync function. So if you look at the blue function over here, it has a not as fast of a roll off. But at beta equals 1, which is this neon blue one, it goes to 0 and stays about 0 right away. So that's very useful, okay? It's also useful if your bandwidth requirements vary. For example, if if your bandwidth is, say, right here, you can adjust beta such that you're still within your band limit, but have faster roll off than normal sync functions. If that makes sense. Okay. Questions? Who's still with me? Any confusion on any topic that they'd like me to go over again? Okay. So now we know a better pulse filter. And so let's take a look at our signal and what happens to it in the channel. Okay. So this is actually take a step back. Oh, I'll explain this. Okay. Having just okay, looking down over here, you can just have the symbol mapping, this pulse shape filter, which is the raised cosine, and then of course modulate, demodulate, and no receiver filter in bit mapping, and that would work perfect, or work okay. Okay, that's a viable solution to your channel. And so, but one thing is we're receiving some noise, and so there's a question of can we do anything, for example, some kind of filter to reduce the impact of noise on our signal when we try and reinterpret it. Okay. So if we were to take our symbols, S of t, and put it through, right, we get our pulse filter convolved with our symbols. That's going to be the signal we transmit. It goes through the channel, and we pick up noise. Of course, we demodulate. And if we have a receiver filter, we can express the output as the convolution of your receiver filter with your original signal plus your receiver filter convolved with your noise. Okay, so a receiver filter is going to have some impact on your noise. And one other thing, to preserve the result that we got before, we want the overall effect of a receiver signal and our pulse filter to be a raised cosine. Okay, that's because we want the output signal to be shaped like that. Okay. So our question is, if we were to have a receiver signal, what would it look like? So there's this idea called matched filters. And I didn't think going through the proof was too important, but more the result. But essentially, if you were to take your receiver signal, the power of that information you want over the power of the noise, right? Your receiver signal convolved with G of t, which is S of t, and pulse shape filter, and convolve over the receiver signal and the noise, you would get that the way to maximize this quantity is to have your receiver filter match the shape of your output signal, except delayed in time first. Okay? What does that mean? Okay. I can find a good way to, okay. This is one way to draw it, I guess. essentially what it's saying is, it's like this asymmetric for visualization's sake. If this is your signal that you're sending, let's say like this. We'll make these isolated. Then, oh, they should be more asymmetric. Sure. Okay. Then we need to convolve it with some kind of receiver filter, which would look like this. Okay. So okay, this is how do I explain this? Okay.
Are these both tangent?
Yes. Okay. So if you're sampling at these points, what it essentially means, if you look back over there, is it should be a time reverse signal of your pulse filter. Why? At time tau, this is your pulse filter, right? And only thing is this is time reversed, okay? So, yeah.
I think once they go through the assignments,
think
they
it's-
would
it's
it would
so
make
hard
much
to-
more sense.
You need to think about this. It took me a while to wrap my head around. Another way to think about it is these are your pulse filters convolve every tau. And so if your receiver filter should be the time reversed of t minus tau, then undoing the convolution, you just have a time reversed pulse filter. About. Okay.
See the reason why this is true?
What?
Any intuitive reason why this is true?
Why this is true?
Yeah.
I think it would.
I can tell you the math behind it. if you
Yeah,
want. Okay.
I was gonna say the same. Like mathematically, it will make more sense to go through the proof and.
Okay. I'll just give you a little breakdown real quick. Okay. Basically, okay, you have your power is going to be expressed by the integral in the Fourier domain, right? Of whatever your receive filter is times you can say your receive signal, right? This is the power of your signal, okay? And you want to maximize this, okay? I don't know, okay. For some reason, actually not for some reason, okay. If you look at this real quick, this whole quantity, I want you to recognize first that this is a dot product, okay? Why does that make sense? Because you're summing over each component in frequency times each other, right? That's what a dot product is. Okay. And so knowing it's a dot product, what you can apply is the Cauchy-Schwarz inequality. What that is the inner product of H and G. Oh, this should be squared, by the way, because this is power. This squared is going to be less than or equal to H, the thing dotted with itself, squared times G. And that should make intuitive sense, right? Integral of this squared should be less than or equal to the integral of H squared times integral of G squared, right? And it's a very common result, or basically this inequality maximizes when H equals G times, or I guess H is linearly dependent on G. Okay, that's what the K is on the slide.
Is that a plus or a multiplication between the dot product H, dot product G?
Multiplication. That kind of makes sense. All right. If this was a discrete thing, you'd have, I think of this as a discrete quantity then. Okay, summation over F. Oh, it should be on the outside. Outside might be confusing. Okay. Can you recognize that's a dot product? Right, dot product is summation between two vectors, A transpose B equals summation over N of AI times BI. That's a dot product. Squared. Okay. And so we use Cauchy-Schwarz inequality. That's a common thing. And then your algebra, I hope you remember it. Very important thing. And it gives you this result. And that maximizes when H equals G. Which can be at any factor, any scale factor. The delay doesn't exactly matter. That's, you gotta go more in depth for that. But I hope that makes sense. Okay. The moral of the story is, it should be time reversed over pulse filter. But given our pulse filter is symmetric, it just equals our pulse filter, right? So on the receiver, we want the receive filter to be the pulse filter. But if you guys recall, we want the whole channel, the filtering of the whole channel to be a raised cosine. Right? You want the symbol, you want y at the end, at the receiver end, to look like this, right? If we convolve it again with some kind of filter, the shape's gonna change. So we want the combination of our two filters to equal this. And knowing that convolution in the time domain is multiplication in the frequency domain, we know that our overall channel filter should be our receiver filter times our pulse filter. And given those two should be equal because they're symmetric, that's HR squared, or assuming they're equal, assuming they're symmetric, that should be HR squared. And therefore, our receive filter should be the square root of our channel filter. And if our channel filter is a raised cosine, then we're going to make what's called the square root raised cosine. I did not put any formulas up here, but it's literally just, if you take the frequency domain representation of this, you just throw a square root on top. That's it, okay? It's, you don't ever need to make this yourself. You can just put it up in MATLAB, and it'll make it for you. Yeah. So what this means is your pulse shape filter is a square root raised cosine. Your receiver filter is a square root raised cosine. And the combination of the two creates a raised cosine, which is very nice for intersymbol interference. Characteristically, the behavior of a square root raised cosine is similar to a raised cosine with a roll-up factor, which they call alpha. It's basically the same thing. And so, a nice visualization, this is what you'll be doing in assignment 5, is this. You have your symbols. You convolve it with the square root raised cosine, and it creates this wave down here, right? We don't need to have intersymbol to account for intersymbol interference while it's going through the channel. All that matters is the signal is clear on the output, right? And then once you convolve it again with the square root raised cosine on the receiver end, you get this nice, very clear signal. And yeah, all you gotta do is just sample right. That's a problem for later, sampling right. Yeah. Any questions? Actually, I'll recap first. Overall process is we're gonna take our bits, map it to symbols, as we saw in a constellation diagram. For us, we're using BPSK, so you either have a phase of 0 or 180. And then we take those, we're gonna represent it as delta functions, and then we convolve it with our pulse shape filter, which is the square root raised cosine filter. Then you're going to modulate it to 1 megahertz, because that's the frequency the microcontroller sends. It's going to travel through some channel, demodulate it through multiplying it by a cosine and a negative sign, right, to retrieve your I and Q components. Apply another root raised cosine, and you sample and map it back to bits. And that's the bulk of it. We're going to go into how to account for non-idealities in upcoming lectures. But this is a very general procedure of what you will be doing. Any questions? You have the slideshow. I'll show the slideshow, don't worry. Yeah, I understand this is a lot of content. I encourage you guys to take a look at the slideshow again and again to really absorb it.
We'll also share a document that's a little bit more rigorous in math and just goes over the concepts in more detail. So, like especially like for the matched filters. So yeah.
Yeah.
How about that?
We'll see.
Yeah.
Okay. Yeah, thank you.